What this is building up to is a look at circular motion and how that relates to magnetic forces, and then it builds up to a future video where we have a look at the applications. Right, okay, so in terms of current flowing through a wire, okay, we've got electrons flowing through a wire. Electron flow is going this way, therefore conventional current is going the opposite way. If we've got a magnetic field acting into the board on this, prove it to yourself with Fleming's left-hand rule that that is going to go downwards. Okay, so prove to yourself using Fleming that that is going to move downwards. The force experienced is related to the strength of the magnet, so the magnetic flux density, the value of the current, and the length of the wire. Okay, we know from GCSE that current is defined as the amount of charge per unit time, and we also know that velocity is equal to distance divided by time. In this case, distance is the length of the wire, and velocity refers to the velocity of the electrons. So if I substitute Q over T in for the I, and if I substitute length over time in, okay, so length is equal to velocity times time, so if I substitute velocity times time in for length, we end up with F equals B, Q over T in for the I, and V times T for the L. Okay, we can cancel these two T's, these can cancel out, so we end up with the equation in the format F equals BQV. This is the velocity of the electrons, this is the charge, and this is the magnetic flux density. Something I will point out is if it's electron charge, this can be replaced with a lowercase e rather. So if you see F equals BeV, BeV is referring to where the E is the electron charge, which is 1.6 times 10 to the minus 19 coulombs. Something to watch out for is it's not always the electrons. Sometimes we will use positive ions. If we use positive ions, then current is in the same direction as what the particle is flowing in. So if it's positive, then current is this way. So if we have a look at this as an example, here we've got the positive ion going this way, magnetic field is going into the board, okay, and then this is going to cause this particle to move upwards, okay. If there is a uniform magnetic field and the values are of the same value, then the particle will move round in a circle. For a more accurate diagram, I should have started the curvature earlier on. Okay, because this particle will be acted on perpendicular, okay, it starts to go into a circle. The centripetal force equation from earlier in the year is force equals mass times by velocity squared divided by the radius. Newton's third law, let's say that centripetal force is equal to the magnetic force, then we can say that mv squared over r is equal to bqv. And what we can do is we can have a look at the relationship of the size and the radius of curvature related to the different values. So, what I'm going to do, okay, mv is on the top, so mv squared is on the top rather, so mv squared is equal to rbqv. One of the v's will cancel, so that can disappear, and that drops from v squared down to plain old v. Okay, and then making radius the subject, BQ goes over here and goes on the bottom, so radius is mv divided by BQ. That means that if you increase the mass of the ion, then what happens is the radius size increases. This means that if you increase the speed of the ion, then the radius size increases. However, if we increase the size of the magnetic field, the radius will decrease in size. The other thing is, if the amount of charge is increased on the ion, then the radius will decrease in size. So radius is inversely proportional to magnetic field, radius is inversely proportional to charge.